All right, so we've talked about some of the different ways that light can interact with a ceramic, and one of those being transmission. And so now let's look at what we call transmission windows. And so, as you know, what we'd call transmittance is basically proportional to the light that is not reflected or absorbed. So it's basically not scattered, not absorbed into the material. And so it's basically if it doesn't undergo one of those interactions with the material, then it makes its way through and is transmitted. And so that's our transmittance. And so this is an example of a clear or a transparent ceramic, in this case, spinel. Okay, so those if it's not transmitted, then in these cases we would consider this losses, right? The signal is weakened, or in the case of optical properties, we call this attenuation, or light that is attenuated. So these are just weakened light. So this is basically all of our losses that we have. So absorption and scattering, all of those are attenuations of the light because they're not allowing the light to be transmitted. And so again, A here is very transparent. The transmission is high, whereas B, there's a lot more attenuation or loss of the signal, and that could be from absorption, that can go into heat, or it could be deflected, scattered in some way so that it doesn't make it through the ceramic. All right, so for these materials that are known to be transparent, it's also important to specify where they are transparent, right? So in these previous examples I showed you, we're looking at this material, and we're looking at either natural light or artificial light, and so we're looking at visible wavelengths, right? And so it's transparent to that light. But there are going to be some other applications where a material may be transparent, but not necessarily in the visible spectrum. And so this is why we often plot the fraction that is transmitted. So 1 obviously being everything is transmitted, and then 0 being nothing makes it through, as a function of wavelength. So a wavelength of our light. And so here, the dashed lines on this graph indicate the visible range. And so those are materials that we would classically think as being transparent. But you can see from this plot, there are other materials that maybe are better in the UV range down here, or the IR range up here, right? And so there are going to be different applications for where that is important. What wavelength is something transparent over. And so that's where we get this transmission range, or sometimes referred to as a transmission window. All right, so we can also look at it in a slightly different way. So this is looking at that same kind of plot, but a lot of different materials, and we're still looking at it as a function of wavelength down here. And so this kind of, if we look at these materials, we see that quartz, fused silica, those types of things are sapphire as well, diamond, all of those are optically transparent. Other ones that maybe you aren't as familiar with, but if you look at sodium chloride, if you have a large crystal of sodium chloride, that should be clear as well. But also there's other materials, right? So in the UV spectrum, there's only a limited number that are transparent, like lithium fluoride, again quartz, sodium chloride, sapphire, some of these chlorides and fluorides down here. And then there's obviously a lot that are transparent in the infrared or far infrared range. And so this gives you that information. And you can see that some aren't continuous. So silicon, we don't think of silicon as a transparent material because, again, if you see that, there's no transmission in the visible spectrum, but it is good for IR or infrared spectrum, where you see a signal here. And also, there's another part that has transparency here in the far infrared, but you can see that there's a gap, and so that's also common as well. And you can see that diamond down here is transparent in the visible spectrum and has a very wide range of transparency. So diamond's a very good transparent material because of this range. And so that's what this kind of shows us, is where we have transparency. Okay, and so again, transparent materials are going to be when we have the absence of those effects like absorption or scattering. And so here, this is looking at the instant intensity versus the reflected intensity. And again, this is as a function of, instead of wavelength, we're actually looking at photon energy, but you can relate the two very easily. And so in this case, since this is looking at what is reflected, any peak that we see or anything that goes above zero indicates reflection, right? So here we actually have different phenomenon occurring, either absorption or scattering. And so it's hard to see, but right at zero, there's actually absorption, edge absorption in this material. At about 2, there's what are called F centers, and we're going to talk about those a little bit more in the next section. And also up at the higher EV, our energy, we have UV excitation of various materials, and this could be from valence to conduction band materials. So essentially, electrons are promoted from one to the other because of this high energy. So we see that the materials are strongly dependent on wavelength, and so there are going to be different features that occur within the material at different wavelengths or energies based on how that light interacts with material. So these are all kind of absorption or scattering effects. And so that would greatly decrease the transmission. And so let me sort of go back to one slide here. And so for the most part, like if you look at quartz or window glass here, in the visible range, they're almost 100% transparent. But if you look at the higher end here, you see that it's not perfectly level, and you see a drop off, and there's peaks and valleys and so forth, right? Those are due to those absorption events, right? So whenever you see a dip or an artifact in that material, that's because of those absorption and scattering events that occur within the material. And so that's going to be dependent on band gap and a lot of other things that we talk about.